So now what Faraday did was, instead of taking a coil and a bar magnet, he replaced the bar magnet by a current carrying coil connected to the battery. This is the setup for it. Okay, so here, what do you see in the setup? What is the change? The change is this coil 1. This is known as the primary coil. Okay, and this coil 2 is known as the secondary coil. So is there something that you can notice about the two coils? Do they look different in some way, apart from the fact that one is connected to the battery and other is connected to a galvanometer? Look at the coils themselves. Do you see any difference between them? Yes, you can see that coil 1 or the primary coil has more number of turns as compared to the secondary coil, which has lesser number of turns. Right? What does lesser number of turns means? Look at this. This has 1, 2, 3, 4, 5, 6, 7. These many turns. And when you count these turns, this is actually less than the turns in the primary coil. Okay. So, what was the experiment that was conducted and what was the observation that was observed from the experiment? So, what was done was, in this coil 1, you can see this key here. So when you disconnect the key, there is no current in the circuit, and when you connect the key, there is current in the circuit. So just think about when the key is not connected, so the circuit is open, so there is no current flowing through it. When you connect the key, that means as soon as the circuit is completed by inserting the key, you will see that there is a momentary deflection in the galvanometer connected to coil 2. So if I write this here, I will write, when key is inserted, I am representing key by K. When key is inserted, that means circuit is completed. There is a momentary deflection in galvanometer. Okay. What does that mean? Momentary means as soon as you connect the key, that means as soon as current is set up in the coil 1, because coil 1 is connected to the battery, as soon as the key is inserted, there is just a 1 second deflection and the pointer in the galvanometer returns back to its original position, just goes to one side and comes back just for a second. Now, when the key is removed from the circuit, again the galvanometer deflects just for 1 second, but this time in the opposite direction. So I write when key K is removed or the circuit is opened, there is momentary deflection in galvanometer, but in opposite direction than before, than the first case. That means when the key was connected. Okay, so what did you see in this case and in the previous case? That there is only a 1 second current produced when there is some kind of change. In the last experiment, we saw that when the magnet is just moved or just taken away, just for that second, there is a current induced in the coil. And in this case, just when the key is inserted and just when the key is taken out, we see a deflection in the galvanometer, a momentary deflection. Okay. So now if you connect this to what you had previously learned, we learned that a current in a conducting wire basically. Okay. So if you connect this now to what you had previously studied, that current in a wire gives rise to a magnetic field, right? So this coil 1 has current in it, right? There is a current I in this coil going through this coil. So there is a magnetic field around this coil, right? We write that there is current in coil 1, therefore magnetic field 2. Right? So when we just switch on the wire, when we just place the key and we just complete the current, the magnetic field is set up. And when we remove the key, the magnetic field also again changes. It goes to 0, right? And we see that current is induced in the coil 2 only when the magnetic field is changing. Once we put the key inside and we keep the key there, there is no deflection in the galvanometer. That means when the current is flowing continuously and the magnetic field is generated continuously in coil 1 due to the current, there is no deflection in the galvanometer. That means a deflection only comes when there is a change in the magnetic field, right? So let me write this point. This is an important point. Current flows in coil 2 only when magnetic field in coil 1 is changing. Why have I written changing? Because only when the switch is placed and the circuit is completed, and only when the switch is removed and the circuit is opened, there are deflections. That means when the magnetic field just comes on and just when the magnetic field comes out, or when the magnetic field is, so to say, turned off or it disappears, only then a current is noticed. That means a changing magnetic field in coil 1 gives rise to a current in coil 2. Now think about this. This coil 1 is like a solenoid. So it is going to have a current like this, right? You remember inside a solenoid, it was like a straight line and like a bar magnet like this, right? So when the magnetic field around coil 1 is changing, obviously there would be some effect on coil 2 also, right? So the magnetic field around coil 2 is also changing because the coil 1 magnetic field has some influence on coil 2 also, because they're just nearby, right? So how do we write this point? We write this as, we know that only when the current is switched on and off, there is a deflection. So we write change in current flowing in coil 1 brings about a change in magnetic field of coil 1. Then we write, as coil 1 influences coil 2 also. What does that mean? That means because the coil 1 and coil 2 are close to each other, that means the magnetic field around coil 1 has some effect on the coil 2 also. There is some magnetic field changing around coil 2 also, right? So as coil 1 influences coil 2 also, so that means around coil 1, the magnetic field is changing and it is causing a change around the magnetic field of coil 2 also, because they are so close to each other, right? If there is a magnetic field changing around coil 1, there is that effect is also felt on coil 2. So we write, as coil 1 influences coil 2 also, there is a change in magnetic field around coil 2 also. This is the important point. This is the actual crux of this statement. This changing magnetic field around coil 2, okay, around coil 2 gives rise to a current in coil 2 only, which the galvanometer detects. Okay, so now I hope it is clear to you what is happening. We are changing the current in coil 1. How are we changing it? We're just switching the key on and off, or we're just placing the key and removing the key. So in that split second, when the key is placed and it is removed, the current is obviously switching, right? The current is changing. That means as soon as the key is inserted, there is a current in the circuit. As soon as the key is removed, the current in the circuit is going to 0, right? So there is a change in the current. And we know that change in current leads to a change in magnetic field also. So the current changing in coil 1 leads to a magnetic field changing in coil 1 only, in the primary coil only. And this change in the magnetic field of the primary coil gives rise to a change in magnetic field of the secondary coil also, because the coil 1 influences coil 2 also. And the change in the magnetic field around coil 2 is the reason for the induced current in coil 2, which the galvanometer detects. Okay, so make sure you know this step by step, like what is happening because of that, then because of that what is happening, and what is the end result. Okay, let's move on. So what is electromagnetic induction? What we just studied with the bar magnet and the coil and two coils is this what comes to. This is what is finally comes to. Okay. So what is electromagnetic induction? Let's read in your PPT and then I'll explain. So it says the process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. So what happened in the second experiment that we did? We changed the current in the coil 1, and because of that the magnetic field in the coil 1 changed, and because of this changing magnetic field in coil 1 a current is induced in coil 2. This process is known as electromagnetic induction. Okay, so we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. So this part, moving it in a magnetic field, this part is the experiment 1 that we did. How? Because we had a coil and we were bringing a bar magnet close to it and taking it away from it. So the bar magnet has some magnetic field, right? So we are kind of moving it closer and far to the magnetic field. So that is what we were doing in experiment 1 with bar magnet. Bar magnet and coil experiment, right? Faraday's experiment. And by changing the magnetic field around it, you can explain with the experiment 2. The two coils. Okay, so I hope this concept is clear to you now, because this is what we are going to use when we are going to study the electric generator. Okay, like we studied the motor, now we are going to study a generator. Okay, now the interesting thing is Fleming didn't just make one rule, Fleming made two rules. You remember the first rule, we had used magnetic field, current and force. That was in case of when we had the force, we had the magnetic field, we had the current, and they were mutually perpendicular. So if you had any two, you could find the third. That was the Fleming's left hand rule. Now because you already know how to hold the fingers in the left hand, I don't need to explain it to you again. So I can just tell you what each finger stands for in the right hand rule. So let's read. It says that Fleming's right hand rule states to hold the forefinger, your index finger, the middle finger and the thumb of the right hand mutually perpendicular to each other. Look at my hand like this. So what happens? The forefinger points in the direction of external magnetic field, like it's given here, direction of field. So if you remember in the last experiment also, in Fleming's left hand rule, the forefinger or the index was towards the magnetic field only. So that hasn't changed. Next we learned that the thumb points in the direction of motion of conductor. So here it's written direction of force. So instead of direction of force, you can write the motion of conductor, because that is more relevant to what we had studied in our experiments also. And instead of direction of current, write direction of induced current, because now we are studying about electromagnetic induction. We are inducing a potential difference and then in turn inducing a current. So direction of induced current. Okay, so you can remember it because it's pretty similar to your left hand rule. In the left hand rule also, your index finger was in the direction of the magnetic field. Here also it's in the direction of magnetic field. Your middle finger was in the direction of current there, so the normal current, but here because it's electromagnetic induction, obviously it is induced current. Here it was force, here the thumb is direction of movement of the conductor. Okay, great. Let's move on now. So the first question says, explain different ways to induce current in a coil. So we are going to write in the answer using Fleming's experiments. We know that the different ways to induce current in a conductor is, if I write it according to the first experiment that we did, which was the bar magnet and the coil. So what did we see? That by moving a bar magnet close to and away from a coil. So what happens in that case? A current is generated in the coil only at the times when the magnet is in motion, right? We saw that as soon as the magnet is brought close and it is stopped, there is no deflection. There is only deflection when the magnet is brought closer, when the magnet is moving closer, or when the magnet is moving away, right? So there is only current generated when there is relative motion. So we learned by moving a bar magnet close to and away from a coil while keeping coil stationary, right? The second was, in this same experiment, we can keep the bar magnet stationary by moving the coil, right? Sorry. By moving the coil close to and away from a bar magnet that is kept stationary. That means the bar magnet is stationary, right? So you can also show this by showing the figure here. You can have this insulating cylindrical rod on which you can wrap your coil, connect it to a galvanometer to detect the current, and have show this bar magnet which is taken close to it. So then you will be able to explain it better. So now instead of just stating this, you can say when we move a bar magnet close to a coil, we see there is a momentary deflection in the galvanometer. Then when we take it away from the coil, there is another momentary deflection but in the opposite direction. In the second point, you will write that when the coil is brought close to the magnet, there is a momentary deflection, and when it's taken away, there is a momentary deflection. But when both the magnet and the coil are kept at the same position, there is no deflection. That means only when there is relative motion between coil and magnet. This is the point for both 1 and 2. You will write this point in point 1 also, because there is only current generated when there is relative motion between the magnet and the coil. Great. This last point was by changing magnetic field around a primary coil by changing the current through it. How do we change the current? We change the current by putting the switch on and off. You can also change it by increasing the current flowing in the circuit by replacing the battery. Then also you will see a momentary deflection. By changing the current through it, changing magnetic field around the primary coil by changing current through it gives rise to induced current in secondary coil. Now you can't just say primary and secondary just like that. You will have to draw it. You will have to draw this coil with more number of turns, connected to a battery and a key, right? Connect this like this and have one more coil near this but with less number of turns and connected to a galvanometer, right? And explaining using this figure, you will write coil 1 here, you will write coil 2 here, and you will write this is the primary coil and this is the secondary coil, and then explain it. Okay, I hope this is clear to you now. So students, this is all for this video. In the next class, we are going to use all the concepts that we studied today of electromagnetic induction in the study of the appliance electric generator. Okay, so make sure you are thorough with the Fleming's right hand rule. You are thorough with the concept of electromagnetic induction and how all it can work. Okay, I'll see you in the next class, students. Thank you and take care.